Hello, hello Year 9 and 10. I'm Mr. Devlin, for those of you who I haven't taught. This is the second physics online lesson that we're putting out from St. Leonard's after the first one that you got from this page. I've chosen to do this revision lesson on CP6 radioactivity because you should all have done it before. You should all have studied radioactivity already, and I know it's a difficult one that people struggle with. So I'm going to try and make it as accessible and as easy as possible. In the lessons coming up in the following weeks, we're going to have more radioactivity lessons, but we'll also have some more probably on physics key skills, the real fundamentals. Okay? So what are we going to go over this lesson? What are we going to look at? We're going to have an introduction to CP6 radioactivity. We're going to see just why I think radioactivity is an awesome topic. Some of the cool things which we study in radioactivity, nuclear bombs, nuclear power plants, things like that. We're going to look at some keywords. We're going to make a mind map. We're going to look at atomic models, the main atomic model that we use for GCSE. And we're going to look at how atomic models have changed through time. I estimate that this lesson will take you an hour to complete. And all that you need is a pen or pencil, a piece of paper or two, and ideally a quiet, clear workspace. Okay? Just as a reminder, because I think there's a bit of uncertainty amongst the students about the work expectations that we have from you, from the SLA Science Department during this COVID lockdown. We would like you to try and complete 3 hours of science work per week. And this can be the revision booklets that we've given you. It can be online lessons that we're putting out, such as this one. Or it can be your own work, for example, a revision using BBC Bitesize or the Oak National Academy or any other resource that you find and like. And if you're struggling for resources, do please get in touch with us and we can point you in the direction of some really good online ones. Okay. So without further ado, let's get started. What I'd like you to do for the starter, as it were, is write down on your paper everything that you can think of when you hear the term radioactive and nuclear radiation. You can also add the LQ, what we will be learning in CP6 radioactivity, or just CP6 radioactivity lesson 1. I'd like you to pause the video whilst you write down everything that you can think of, and then start again and start the video again, and I will let you know of some of the things that I think of when I hear radioactive and nuclear radiation. Okay, you can pause the video now. Okay, so some of the things I think of, if we just use the pictures first of all for inspiration, we've got down at the bottom left, we've got a nuclear explosion. That looks like a nuclear explosion to me, so you can think of there's probably huge amounts of energy involved with radioactivity and nuclear radiation, or there may be huge amounts of energy involved. Here at the top left, we've got Fallout Boy. That's or no, it's not Fallout Boy, is it? I can't remember his name. But anyway, it's a computer game character from the game Fallout, who lives in a radioactive wasteland, a post-apocalyptic wasteland after a nuclear war. So when we're thinking about radioactivity and nuclear radiation, we may think about nuclear conflict and the fact that it has the power to make large parts of the world uninhabitable for long, long periods of time, hundreds or thousands or even tens of thousands of years. In the middle, we've got Hulk. So we might think of radioactivity as causing mutations, which may cause us, make us mutate into superheroes. One of the effects of radioactivity on the human body is to cause errors in our DNA, which can lead to mutations. Unfortunately, most of those mutations are very harmful and may even lead to our death. They are very, very unlikely to lead us to change into superheroes. Down at the bottom right, you may have seen this sign before, the yellow and black one. That is a warning sign for ionizing nuclear radiation, ionizing nuclear radioactivity. And this is a barrel of nuclear waste. You might think of nuclear waste. Some of the other things that I thought of when I think of radioactivity and nuclear radiation, I think of huge releases of energy, either uncontrolled in the form of a bomb or controlled in the form of nuclear power plants, nuclear submarines, and those kinds of things. I think of course, nuclear explosions. I think of the sun, because that's powered by fusion power. I think of nuclear disasters like Chernobyl is a big one, or Fukushima. I think of nuclear waste and how nuclear waste stays radioactive for thousands, tens of thousands of years. And that brings me, one of the things I think of with radioactivity, radioactive and nuclear radiation, is that it can pollute areas for many, many, many years if they become contaminated, if areas become contaminated with radioactive material. Okay, you might have your own as well. If you tried the PQ, that was what might cause an element to become radioactive. It is if it has the incorrect ratio of neutrons and protons, then it will be radioactive. Okay, so let's have a look at some key terms first before we get started. So we talked about what we think of when we think of radioactive and nuclear radiation. The key terms, first of all, because I know that it can be confusing, I just want to introduce you to some. We've got radiation, okay? Radiation means the emission, the giving out of energy in the form of waves or particles. So this could be, doesn't have to be nuclear radiation, okay? Could be the emission of sound energy from a radio, like this, for example. It could be the emission of electromagnetic radiation from a light bulb. You might know it as light, but electromagnetic radiation from a light bulb. To radiate is to give out energy in the form of waves or particles. If you'd like, you can write that term down if you don't have a clear definition in your head. Now, nuclear means from the nucleus, from or of the nucleus, in this case of an atom. Here's Niels Bohr's nuclear model of an atom. We have a small, dense nucleus in the center of the atom made of protons and neutrons, positively charged protons, neutrons, surrounded by electron shells in which negatively charged electrons orbit. Nucleus is the bit in the middle. Nuclear means from or of the nucleus. So, nuclear radiation, next one, is simply the emission of energy from the nucleus of an atom. Now that could be, as we wrote in radiation, it could be in the form of waves, or it could be in the form of particles. But it is the emission of energy from the nucleus of an atom. Okay, just going to move you down a little bit. Let's move on. So, I want us to look at what happens when we start messing around with the nuclei of atoms. Okay? There are very, very strong forces which keep the nucleus of an atom together. Okay? If we think of the protons in the nucleus are positively charged and they're forced in the nucleus very close together, they need a very strong force to keep them together. When we start messing around in that nucleus, maybe we break the nucleus apart, we can release vast amounts of energy, okay? And we're going to look at an example of an energy release of when we start messing around with the nuclei of atoms. Okay, when we watch this video, I want you to try to answer these 4 questions you've got in front of you. What are we watching, number 1? How can we estimate the size of what we are seeing? Is it large or small? 3, are there some things which move faster than others, and what might these be? And then 4, as an extension, how might we estimate how far we are from the center of the blast? Okay, write down those 4 questions, and then we're going to watch the video, and I'd like you to try to answer them. Okay, if you've got those 4 questions down and you're ready to go, then here we go. Otherwise, pause and write them again. Here we go. What are we watching? So those are full-sized ships. They are full-sized battleships. This was made in about 1950s. Something coming towards us very fast. Oh, and then we hear it. And if you look at the ships, there is something else which is coming towards the ships. What's that? It's engulfing them, completely destroying them. Okay, we'll pause that here. Okay, so what are we watching? I think hopefully you will realize that we're watching a nuclear explosion. That was a nuclear weapons test. Number 2, how can we estimate the size of what we're seeing? Is it large or small? As I said, those ships are full size. They are not model ships. And you might not know the exact size of a battleship, but you probably know that they're quite large. If we think of I can give you an estimate for the size of a battleship. That's maybe 300 to 400 meters long. If we think of those ships as 300 to 400 meters long, then we can see that that explosion was kilometers across. So vast. Are there some things which move faster than others? What might these be? What I thought coming towards us, first of all, we could see ripples on the surface of the sea, which then seemed to hit the trees in front of us, blowing the trees, and then we heard the bang. That was a pressure wave, or a sound or a pressure wave, which came with the explosion, okay? So it's a sound wave and a pressure wave, the same thing. If we then looked at the ships, you could see after the sound wave, there was a water wave, which was engulfing the ships, but it traveled much slower than the sound. Speed of sound in air, we know, is about 700 meters per second approximately. So, the extension, how might we estimate how far we are from the center of the blast? We can use speed equals distance over time, if you remember from motion. I've just told you what the speed of sound in air is. So we've got the speed. You can time it from when you see the explosion, from when we saw the sound wave get to us, and then we heard the bang. So that'll give you the time. You can use the speed and the time to calculate the distance. We're approximately 5 kilometers away from the epicenter of that blast, if you calculated that. Okay, moving on. So we can see that there is a vast amount of energy, a huge amount of energy contained within nuclear fuel that we can release, either in an uncontrolled manner in a nuclear explosion or in a controlled manner in a nuclear power plant. Just to show you, you don't need to remember this, but I think it's pretty incredible in a way, just how much energy there is in nuclear fuel or nuclear explosives, okay? I'm going to compare it to common food and fuels. Okay, here we go, we've got a carrot, and I found it out in kilojoules per gram. So for each gram of carrot, how many kilojoules of energy can we get? In a carrot, you've got 1.73 kilojoules per gram of carrot. Don't worry too much about the units, let's just think about the number. Here we go, next, we've got Big Mac. You might like to guess before we go for it. I'm going to go for it now. Big Mac, 10 kilojoules per gram. As we might expect, a lot more energy per gram of Big Mac than there is in a carrot. Cheese. Now, cheese is largely made up of fat. Fat or lipids is one of the most energy-dense food sources that we can use as humans. So it's not surprising cheese has a very high energy density. It is 17. So about just over or just less than 10 times the energy density of carrots. Shouldn't come as any surprise. Wood, we can't eat wood, of course, but we can burn it in a stove, use it as a fuel. Nice dry wood has 20 kilojoules per gram of wood. It's an excellent fuel. Not quite as good as petrol though. So there's a reason why petrol is such a wonderful fuel and why we use it to power most of our cars. And that's because it's incredibly energy dense. Look at this, 46,000 joules, so kilojoules, 1,000 joules, 46,000 joules for every gram of petrol. It's also a liquid fuel, which makes it very easy for us to get in and out of our cars and to transport. TNT is a common explosive. I was very surprised by this. I was researching this and wanted to know how much energy there is in TNT. It's tiny, 4.6 kilojoules per gram. So the amount of energy per gram of TNT is very small. However, it's released very, very fast. Okay, and that's what makes TNT a fantastic explosive. Now, finally, we have nuclear fuel or nuclear explosive. You might like to have a guess how much it is. You can have a guess now. Hopefully you've had a guess. I'm going to give you the answer now. It is 300 million kilojoules per gram. Okay, that is an absolutely insane amount of energy per gram. So that's why with quite a small bomb, we can create an explosion like the one that we just saw. It also means we can use a small amount of nuclear fuel to create a huge amount of electrical energy or thermal energy if we release it in a controlled manner. So, just as an example, this is a nuclear submarine. There's so much energy. A nuclear submarine means it's powered by a nuclear reactor. So the nuclear reactor needs fuel. There's so much energy in nuclear fuel that a 2 meter cubed amount of fuel, or volume of fuel, is enough. So that's about the size of a teacher's desk. Think about 2 meters long by 1 meter by 1 meter. Is enough to power a whole huge submarine like this for its entire operational lifetime, for 40 years. So 40 years of sailing around the Earth. Think about that. 2 meters cubed, an amount of a volume of fuel, same size as a teacher's desk, is enough to power a huge submarine like that for 40 years. So we're dealing with something with a huge amount of energy. Now, again, not going to be tested on this, but I wonder if any of you recognize this. Give you a second, and I'm going to let you know. You should recognize it because it's very close to us in Hastings. This is Dungeness Nuclear Power Station. It's huge. I think you'll agree. You can see the size of the cars there. It generates 1,320 megawatts of electrical power. Now, you might not know how much that is. That's okay, because I'm going to tell you. It's enough to power 1.3 million homes. Okay, so this it looks like a large site, but in the grand scheme of things, it's not that large. It's powering so many homes. The same as 500 wind turbines. And unlike a wind turbine, this power station operates through the night, through the day, when the wind is blowing, when the wind is not blowing. It's an excellent, excellent source of baseload power for our national grid to power our houses and for our electrical needs. Just to let you know where it is, how close we are. There's Dungeness. Here it is. it's the other side of Rye from us. There's the power station. It's about 25 kilometers away from Hastings, which sounds like a long way, but really in the grand scheme of things isn't. So if nuclear power can provide all of this huge amount of power, why don't we get all of our power from nuclear energy? It doesn't create carbon dioxide emissions like a fossil fuel power plant does. So why don't we use it more frequently? There are some quite significant issues with nuclear power. When it goes wrong, and this is a GIF of a nuclear explosion, but I think it's a good illustration. When nuclear power plants go wrong, they go very, very wrong, okay? The worst thing that can happen in a nuclear power plant is something called a nuclear meltdown. It's when we lose control of the nuclear reactor at the center of the nuclear power plant, and we're unable to cool it, and we have an uncontrolled nuclear reaction, an uncontrolled release of energy. I'm not going to watch it, this YouTube, but I encourage you to pause the video and watch the YouTube. It's the trailer for the HBO series Chernobyl, which was released last year. And those of you who I have taught this topic will have already watched this trailer, but I encourage you to watch it again. It's one of the highest rated shows last year from HBO, very, very good. And it shows you the events around the nuclear meltdown at Chernobyl nuclear power plant in the Ukraine. The area around the Chernobyl nuclear power plant was abandoned during this nuclear disaster. It was evacuated because the surrounding area became so contaminated. It is still evacuated to this day. And the evacuation zone is more than 50 kilometers across. So if we go back to this map, if Dungeness were to explode, or were to have a nuclear meltdown, sorry, in the same way as Chernobyl, then we may well have to evacuate Hastings and may not be allowed back for many tens or hundreds of years, which is the case in Chernobyl. I encourage you to watch the trailer and very much to watch the series. It's on Now TV, I believe. Okay, now it's time for you to do something a little bit more involved. As this is a revision and introduction lesson, I'd like you to do some revision. I want you to write CP6 or SP6 if you're a triple student, radioactivity in the middle of a new blank page. Around the outside of the page, I'd like you to write the following titles, subtitles. Okay, so types of nuclear radiation, atomic models, background radiation, emission, absorption, and ions, isotopes, radioactive decay and AZ notation, half-life, and dangers of radioactivity. When you've done that, I would like you to go on BBC Bitesize. The link is below, so you can just write that down and copy it into your browser. And I would like you to try to find out some information about each of these headings. I'm going to tell you briefly the kinds of information I'd like you to find out. You can, of course, find out more, but this is what I'd like you to try and find. Okay, and you may also remember it from when we studied radioactivity before. So for types of radiation, what are the three main types of nuclear radiation? You can also write down their characteristics. Atomic models. Can you find 3 different atomic models? You can search for these online as well as just on BBC Bitesize. You might also like to define what is an atomic model and find 3 different ones. Background radiation. Where does it come from? What is it? And where does it come from? Emission, absorption, and ions. How do atoms absorb and emit electromagnetic radiation? Also, what is an ion and how do atoms become ions? Isotopes, this topic. What is an isotope? Just a definition, and maybe give some examples of isotopes. Find, for example, the different isotopes of hydrogen or of carbon. Radioactive decay and AZ notation. What is radioactive decay? And what is AZ notation? You will find that on the BBC Bite-Sized Topics. And then finally, what effect does radioactive decay have on the atomic mass and the atomic number of an atom? Half-life. What is the half-life of a radioactive element? What does half-life mean? Try and find that out. And then finally, dangers of radioactivity. How can radioactivity harm us? And what steps can we take to avoid that harm? Okay, I think that should take you about 10 to 20 minutes, let's say, okay, if you're doing it properly. It'll provide a great revision exercise for you for the CP6 or SP6 radioactivity topic. If you're going to do it, I'd like you now to pause the video and to make your mind map. You can pause your video now. Okay, if you've unpaused it, let's move on. Very well done for making your fantastic mind map. Oh, just pop back. If you've got the basics of these topics, then you've got pretty much everything there is in CP6 radioactivity. So well done. Here we go. Okay, so that's our mind map. We're now going to look at atomic models. Okay, so this is the Bohr atomic model of a nitrogen atom. A model of an atom is simply a scientific model, is a representation of an idea, an object, or a process that's used to describe and explain the phenomena that the phenomena associated with it that we can't experience directly. So we can't see an atom, so we've made a model of an atom, okay? This is Bohr's model of the atom that he came up with to explain the observations that he made. Okay, so the parts of the Bohr model of the atom, which hopefully you're familiar with, we have a small dense nucleus in the middle, that's this bit, which is made up of neutral neutrons, that's D, positively charged protons, which are C, there, sorry I'm in the way there. We have around the nucleus, we have electron shells, which are indicated by A, and the electrons orbit in those shells, which are indicated by B. Electrons have a negative charge. Most of the atom, the vast majority of the atom, is empty space. So everything which is not a proton or a neutron or an electron is just empty space. Now note, it's not drawn to scale. In actual fact, the atom would be much, much, much smaller, and the nucleus would be much, much, much smaller than it's drawn here relative to the electron shells. How much smaller? I hear you cry. Okay, so let's have a look. I just want you to use this as another model to help you imagine just quite how small the nucleus is relative to the atom. If we were to take this atom and we were to blow it up to the size of this atom here, and we were to blow it up to the size of the London Eye, it might be called the Coca-Cola London Eye now or something, I don't know, then how large would the nucleus in the middle be? I'll tell you. The nucleus would be the size of a garden pea, okay? So the nucleus is hugely smaller. It's very, very, very much smaller than the atom itself. And atoms themselves aren't massive. They are very, very small. How small? 1 × 10 to the -10 meters in diameter. How big is that? That's the SI way of writing diameter, okay? How small is that? We'll go over that in the key concepts lesson next week or the lesson after. If it helps you to remember, it's 1 × 10 to the -10 is 0 point followed by 9 zeros and then 1 meters. A very small number. How about the nucleus? The nucleus is much, much smaller, and again, we would say it's 1 × 10 to the -15 meters in diameter. That is 0 point followed by 14 zeros and then 1 meters. Okay, that's my introduction of the atom. Now it's your turn to do something. I'd like you to have a go at these 5 questions. Number 1, what are the point parts labeled A, B, and C, and D? There's an extension, you can add their mass and their charge. Number 2, how big is a typical atom? Number 3, how big is a typical nucleus? Number 4, what is most of the atom composed of? And number 5, where's most of the mass of an atom? Okay, you can now pause this video. You can pause it right now. Okay, if you've unpaused it, we can now go through the answers. Let's see if you were right. So, A, B, C, and D. A was the electron shell, B was an electron, C was a proton, D was a neutron. How big is the typical atom? We've said it already, it was 1 × 10 to the minus 10 meters in diameter. Number 2 is 1 × 10 to the minus 15 meters in diameter. That was the diameter of a nucleus. Number 4, most of an atom is made of empty space. It's nothing. Number 5, the nucleus. Oh, where is most of the mass of an atom? It is in a nucleus. 99.999% of the mass of an atom is in its nucleus. Okay, now we've got one more exercise to do, I promise, last one, and then it'll be our lesson, our revision lesson over. Now, this one is quite information dense, but I think, but it's not too hard, okay? So I think you should be able to cope with it fine. So, how has our understanding of the atom changed over time? We just saw the Bohr nuclear model. That's the one that most people think of when they think about an atom. And it's the one that we use, the most advanced one that we use at GCSE level. If you go to A level, we'll use more advanced ones. But if we go back through time, we'll see that in earlier times, people didn't have such a sophisticated understanding of the atom, but they developed models to explain what they could observe about the atom. What I'd like you to do, this is time for you to do a little task again, is to take another full empty page, draw 2 lines in it, splitting your page up into 4 quarters. Write out in your quarters, these are 4 different nuclear models that we have as our understanding of the atom has moved on. So write out in each one a little subtitle: Dalton, J.J. Thomson, Rutherford, and Bohr. We're going to watch a video about the different, obviously watching a video right now, but a video within a video. We're going to watch a video about how our understandings have moved on through time. And I would like you to try and get the following information from that video. If you don't get it, don't worry. I'll give you some of the notes afterwards. However, try to get it as you go along in the video, pausing it if necessary. I want you to get, for each model, the date. When did the scientists come up with it? What's the name of the model? What are its key features? And what was the experiment or observation? So that's in purple, so that's an extension task. That's for higher or triple students. What was the experiment or the observations of the scientists which made them come up with their model, which led to their model? Okay, so you can see the link to the YouTube video here. Okay, we're not going to watch it in this video. I would like you to pause this video lesson to type out the link here into your browser to watch the video and to try and fill in your page with this information. Okay? I would like you, afterwards, I will give you some answers, but I want you to do that yourself. Okay? It shouldn't take you, the video is about 6 minutes long, so it should take you 10 to 15 minutes. Okay, I want you to pause this lesson and start the video and get the notes. You can pause it now. Okay, if you've resumed the video, welcome back. Let's go through some of the information that I got for these models, okay? You might have other things from that video. It's got a lot of information in it. It's a great video. Let's have a look. We've got Dalton, 1803, sorry. He came up with just a Dalton model, where atoms are small, hard, and indivisible. And he developed that because he saw that there was a fixed whole number ratio of atoms in chemical reactions. J.J. Thomson in 1897 came up with the plum pudding model, where the whole atom is positive, but it has negative electrons embedded within it. And he got that from experiments with cathode rays. He discovered particles smaller than atoms, which were negatively charged, and he called those electrons, which he put in his model. Then Rutherford came along with his model in 1909, which he called the Rutherford nuclear model, where there's a dense positive nucleus surrounded by the electrons. And he came up with that in his gold foil experiment, where he fired positive alpha particles at gold foil, at a thin gold foil. He expected, if it was J.J. Thomson's model, he thought that the alpha particles would just go straight through, but instead some of them bounced right back. Now that showed that them bouncing back showed there must be a small, dense, positively charged nucleus at the center of the atom, and that's why he developed his model. Then Bohr came along in 1913 and came up with his planetary model. The key feature of that is that the electrons in the model orbit at fixed energy levels, or shells. The electrons further from the atom have more energy than those closer in. Further from the nucleus, have more energy than those closer in. And he developed this model because it explains why each atom has a certain number of electrons available for chemical reactions, also why each element emits certain colors of light. Okay, that was a lot of information, so apologies for that, but that's it in terms of new information or going over information. Now we're on to the final task. And you've got a bit of help here, as you can see. Unfortunately, my video is now covering up various important parts. I'm going to drop me down to there. Okay, so if you are a combined foundation student, then I'd like you to try to do the silver 6-mark question, which is there. Describe the 4 main atomic models and their key features. If you're a combined higher or a triple student, have a go at the gold question. It's up there. Describe how atomic models have changed over time and how evidence has helped. Okay, you can go for 6 points or you can go for more. We've given you quite a lot of help there with the success criteria. Okay, so work through the success criteria and try to write a coherent 6-mark question answer, and try to pay attention to your spelling and grammar as well if you can. When you've written your answer, you can either do it on a computer or you can do it on a piece of paper. You can, if you've done it on paper, you can take a picture of it. You can submit it by going to showbe.com, that's here, showbe.com, and typing in the class code HZ9N9. Okay, if you type in that class code, you'll see there is an assignment set from last week, and there's this question set for this week. You can then submit your answer, and one of the teachers from the school, from the science department, probably myself or another science teacher, will give you feedback on your answer so you can get as perfect an answer as possible. Okay, so that's the end of this lesson. Keep tuning in. In following weeks, we're going to have a couple more radioactivity revision lessons, and we're also going to have a key skills lesson as well. Okay, thank you very much for your time. Thank you very much for your effort in these extraordinary times that we find ourselves in. Looking forward to seeing you again in the coming videos, but also, of course, when we come back to school. Wishing you all the best. Bye now.